Hello again. Welcome to another lesson in geometry. Today we are covering section 11-7, areas and volumes of similar solids. So we have some vocabulary to warm us up here. So review. Complete each statement with the appropriate word from the list and use each word only once. So there are several similar house styles in the neighborhood. Okay. The sequel may end similarly to the original movie. There is not one similarity between the first and second drawings. And you could find several similarities between the two video games. All right, so our vocabulary builder here, scale factor. Scale factor for similar polygons is the ratio of the lengths of their corresponding sides. The scale factor for two similar solids is the ratio of their corresponding linear dimensions. Okay, that's their definition. And the example is the scale factor of a map might be 1 inch to 5 miles. So it's the ratio of their corresponding parts. So the 1 inch is going to be the distance on the map, where the 5 miles is going to be the distance in the real life. Okay. All right, so use your vocabulary, write true or false. You can find the scale factor for any two figures. It's going to be false. Okay, you might not be able to get the scale factor. You might not know which sides to use because they might not be similar figures. Okay, you can find the scale factor for similar figures. This is true. Okay, so it would be hard to find a scale factor between a square and a circle. We don't know which parts to compare. Okay. All right, you can write a similar factor, a scale factor, as a ratio of A to B or as a fraction of A to B. This is true. Okay, remember, a scale factor is just a ratio comparison of the two things. So in this case, we can compare with the colon, or we can compare here with the fraction. Scale factor is always written as a ratio of A to B, and that's false. We could write it as a fraction. We could also do B to A, so there's many ways to do it. All right, let's flip it over and check out page 2. Okay, identifying similar solids, problem number 1. So are the two cylinders similar? If so, what is the scale factor of the first figure compared to the second figure? Underline the correct words to complete each sentence here. So you can check whether prisms are similar by comparing the ratios of 3 dimensions. Okay, so you have to compare the ratios of all 3 parts, the left and right, the front and back, and the up and down. Okay, you could check whether cylinders are similar by just comparing 2 dimensions here, because the radius is going to be the same left and right as it is front to back. Okay, always compare the ratios of corresponding dimensions. So we're going to compare the radiuses to each other and the heights to each other in this case. So the ratio of the height of the larger cylinder to the height of the smaller cylinder is going to be 12 to 10, but we could simplify that to 6 to 5. The ratio of the radius of the large one to the radius of the small one is also 6 to 5. Okay. So since we only have to compare 2 dimensions, since the radius is the left and right and the front to back, we can tell right away that these 2 cylinders are going to be similar to each other because their ratios are the same in both dimensions. Okay. Number 14 here, underline the correct words to complete the sentence. The ratios you found in exercises 12 and 13 are equal. So the cylinders are similar. Okay, and the scale factor is going to be 6 to 5. Okay, so to compare for 3D objects, we must compare not only left and right and front and back, but also up and down, all 3 different ways and for all 3 dimensions. All right. Theorem 11-12, areas of volumes of similar solids. So if the scale factor of 2 similar solids is A to B, so that means when we're comparing the left and right, the up and down, and the front and back, they all end up being the same. then the ratio of their areas is going to be a squared to b squared. And the ratio of their volumes is going to be a cubed to b cubed. And we'll do some example problems and show how this works. So complete the model below. Scale factor of similar solids, if it's a to b, then the area is going to be a squared to b squared, and the ratio of their volumes is going to be a cubed to b cubed. Okay. So if the scale factor of two similar solids is 1 to 2, okay, then the ratio of their corresponding areas is going to be 1 squared to 2 squared, which is 1 to 4. So the area is going to be 4 times bigger if than it was before. So here we have 1 to 2, and now it's going to be 1 to 4, okay, 2 squared. If the scale factor of two similar figures is 1 to 2, then the ratio of their corresponding volumes is going to be 1 cubed to 2 cubed. So now it'll become 1 to 8. So we changed the left and right was 1 to 2, and now the volume becomes 1 to 8 for those same figures. Okay. All right, on page 3, we have problem number 2, finding the scale factor. So what is the scale factor of two similar prisms when the surface area of 144 meters squared and 324 meters squared? So we know the scale factor or the ratio of their areas, and we know they're similar, so we want to find the actual scale factor for the two figures. So I can write the ratio of the lesser surface area to the greater surface area. So the lesser one is 144, and the bigger one was 324. And then we can square root both of them to get the scale factor of the figures. Okay, so the square root of 144 is going to give us 12. All right, and then the square root of 324 is going to be 18. So our scale factor for our figure is going to be 12 to 18. Okay, we can simplify that scale factor, of course, and that will simplify to 2 to 3. So given the fact that we know two shapes are similar, and we know that their surface areas, okay, then we can back up and get the scale factor of the shapes. All right, let's take a look at the next question. The volumes of two similar solids are 128 meters cubed and 250 meters cubed. Okay, so we know that the solids are similar, so there should be a scale factor between them, and we know the volumes. Okay, so the surface area of the larger solid is 250 meters squared, and we want to find the surface area of the smaller one. So the first thing we're going to do is find the scale factor, A to B, of the similar solids, and then down here it says circle the simplified ratio of the volume of the smaller solid to the volume of the larger solid. So this is going to be this one. Smaller one was 128 compared to 250. They're both divisible by 2, so this makes 64 to 125. Okay, so that one's no good, and that one's no good. That's the larger to the smaller. Okay, so find the scale factor A to B. So we knew 64 and 125 for the volume. So if we cube both of those, we're going to get 4 and 5. So the scale factor of the solids are actually 4 to 5. Okay. So now we're going to find the ratio of the scale factors for their surface areas. So since the scale factor of the solids was 4 to 5, their surface area should be in a ratio of 16 to 25. Okay. So circle the proportion that compares the surface area of the smaller solid to the surface area of the larger solid. So we're going to compare, let's see, this was the larger one, and the larger one is supposed to go on the bottom each time. So we'll put the 250 on the bottom. So that's good for both of these, but this one doesn't have area, and this one has 250 on the top. So this is our area of the smaller one, we don't know, and then the area of the larger one is 250. So this is the one we want. So we want to solve this proportion. So we have A squared over B squared. That's our surface area, or our area ratios, is x to 250. Okay, and then we can plug in what we knew for our area ratios, which was 16 to 25 is x to 250, and then we're going to solve this. So if we cross multiply, we're going to get 4,000 equals 25x, and then divide both sides by 25, and you're going to get x is 160. So the surface area of the smaller solid is going to be 160 meters squared. So we could double check that. We should be able to compare 160 to 250, and if we reduce that, it should be in the ratio of 16 to 25. And that works fine. I just mark out the zeros, and I get 16 to 25. Okay? So this is our a squared to b squared, which means that a and b in this case would be square root of all of them, 4 and 5. And that's our ratio of our solids. All right, let's flip it over. Okay, so before we go over the last page of notes here, I want to look at just two cubes here and try to explain what's going on. So the first cube is 1 left to right. The second cube is 2 left to right. So the ratio of the left to rights are 1 to 2. Okay. The first cube is 1 front to back, and the second cube is 2 front to back. So the ratio of front to back is also 1 to 2. And the first cube is 1 up and down to 2 up and down. So a ratio of up and down is 1 to 2. So that checks all three dimensions, and they all are the same ratio. Therefore, these cubes are similar, and they have this scale factor. Okay. Now, we can also write a ratio for their areas. If you have the surface area of the smaller cube, there are 6 sides, and they all have an area of 1. So 6 times 1 will give us 6 for our surface area. So this is the scale factor for area. Okay, so what ratio are they in? And for the other one, there are 1, 2, 3, 4 squares on each side or each face of the cube, and there are 6 faces. So 6 times 4 gives me 24. If we reduce this, we get scale factor of 1 to 4. Okay, and then we'll do volume. Volume for the little one's easy. There's only 1 cube. Okay. For the big one, there is 1 here, 2, 3, 4, 5, 6, 7, and 1 tucked in the bottom there for 8. So 8 cubes make up that. Okay. So our volume is 1 to 8. Okay. If we take a look at what we were talking about before, if the ratio solids is 1 to 2, then their area should be 1 squared to 2 squared. We've verified that already, 1 to 4. And their volume should be 1 squared to 1 cubed to 2 cubed. And we verified that already, which is 1 to 8. So when we're comparing things for length and width versus area versus volume, we have to do squaring and cubing to make it work. All right, let's take a look at that last page now. Problem number 4. A marble paperweight shaped like a pyramid weighs 0.15 pounds. How much does a similarly shaped marble paperweight weigh if each dimension is 3 times as large? So the scale factor of the small paperweight to the large paperweight is going to be 1 to 3. We're going to make each one be 3 times bigger. Okay. So let x equal the weight of the larger paperweight. Use the justifications at the right to find the value of x. So 1 cubed, okay, to 3 cubed. So our dimensions are 3 times bigger, but the cubic part's going to be 1 cubed, and 3 cubed is going to be our ratio. Okay, and then we knew our weights were 0.15 and our unknown weight. So 3 cubed will give us 27 here. And then we can cross multiply. 27 times 0.15 will give me 4.05. So the paperweight that is 3 times as large weighs 4.05 pounds. So it went from weighing 0.15 all the way to 4.05, okay, which is 27 times heavier. And that's because the dimensions were in 1 to 3 ratio, but the volume was in a 1 to 27 ratio. So we have to multiply it by or 27 times as big. Okay. All right. Our lesson check here. Do you understand? So two cubes have similar areas of 49 centimeters squared and 64 centimeters squared. Your classmate tried to find the scale factor of the larger cube to the smaller cube. Explain and correct your classmate's error. So understand the correct words to complete each sentence. So the larger cube has the greater surface area. Okay. The scale factor of the larger cube to the smaller cube is greater than the scale factor of the smaller cube to the larger one. Okay, so if we're doing scale factor of larger to smaller, we want to make sure it's greater than the smaller to larger, of course. Your classmate found the scale factor of the smaller cube to the larger cube. So he did it in reverse of what they asked for. Okay. So find the correct scale factor. So begin with the proportion a squared to b squared. And we were supposed to find the bigger to the smaller, so 64 to 49. Then we square root all those and we get that's 8 to 7. So our scale factor of the larger to the smaller is 8 to 7. And that makes sense because he wrote the scale factor of the larger to the smaller is 7 to 8. But 7 is smaller than 8, so that couldn't have been right. Okay. All right, let's take a look at our last bit here. Check off the vocabulary words that you understand. So similar solids, scale factor. Okay, hopefully you're on both of those. Rate how well you can find and use scale factors of similar solids. Hopefully in here, but you might need to watch this video again. It's got some tricky stuff in here. So just remember to go back and look at this page here, and it helps kind of explain why, if a scale factor is 1 to 2, the area would be squared of each of those, and the volume would be cubed of each of those. Okay, so that's the important thing in here.